It's time for Mr. Bernhard Wiedemann to talk about openSUSE on ARM.
Yes, thank you very much for coming. I'm from Nuremberg, working for SUSE, and I have spent some time working on ARM because I have some devices at home, like a Raspberry Pi, which I wanted to work with openSUSE. So I will explain how we built ARM with our open build servers, how you can build your own software for ARM, even if you just have an Intel machine at home, and maybe some more if you have questions. So, and we just start while we do our setup for the video, which didn't work on my laptop, and others didn't have LibreOffice on it, so it's a bit complicated today. So, for the start, we have the open build service, which is very nice software where you have one source code package with a description how to build it and how to install it. And there we added during the last 2 years support for ARM. And when you want to build for a new platform, you usually try cross-compiling, which means you run a compiler on an Intel platform that produces binaries that are meant to run on ARM. And that works very well for building a kernel and a glibc and a GCC because these packages are made to be cross-compiled this way. But it does not work for all packages because some packages have a tool that is compiled during build time and that needs that tool to be called during build time as well, so you cannot build this tool for ARM because then you cannot run this binary on your Intel machine. Yeah, and these packages are very hard to do usually, so we did a trick for building. Yeah. What? We have half an hour today. Yeah. So, yeah, we have some time left. Yeah, as a cross-compiling, we did a different thing using qemu, and qemu can emulate a whole CPU. So we set up a change root environment where we have all the ARM packages in there, and there we install a compiler for ARM and bash for ARM and an RPM for ARM, and we built everything as ARM binaries. And the only downside of that is that it's very slow because it's emulating the ARM CPU on an Intel host machine. And when you want to compile, you spend a lot of CPU cycles compiling. So it took maybe several months to get factory packages built. And that was too slow. So we did some nice trick there, which was codenamed qemu Excel. And that involved one tiny patch to qemu, which was when a program in this change root. Cool. We got slides. Better than mine. Yeah. So this nice patch for qemu was that whenever there's an exec call in a program telling, okay, and now run this program, like run user bin GCC, it would check in another alternative path under /emul /x8664 if it has there a user bin GCC, and if it has, it runs this native binary with the native libraries next to it. And then the compiler was much faster again because it's just a native GCC binary running. And that sped up factory building by a factor of 5 or 6 maybe even. So it only took a week to build a whole factory tree then with this qemu Excel trick. Yeah, and the second part of qemu Excel was a package that contains this cross-compiler under the /emu path, so that it would be used by the acceleration layer. So, and finally, when we had all these nice tricks set up, there arrived new hardware from Samsung, which was called Exynos boards, and they had Cortex A15 CPUs. And these Cortex A15 CPUs were able to run KVM virtualization, which is how we normally do building in OBS, because of the separation, so that the code that's building cannot do any harm to the system and to the network. So when we had that hardware, we could build ARM natively on these ARM boards, on the Samsung Exynos boards. And oh, there's something. Yeah, never mind. Yeah, so on Cortex A15 we could use KVM to just build in a virtual machine for the separation and have a clean build. The idea is to have a clean build, so no downloading from the internet, because otherwise someone takes a site down and you can't build anymore, and you don't want that. You want reproducible builds in OBS. So we are building from the source packages that we have there and from the binaries that were built before, like the binary GCC that's needed for building. So meanwhile, we have over a year, maybe even 2 years, our ARM builds running. We have openSUSE 12.3 built completely for ARM and released as part of the 12.3 release, and we have some ARM v6 for the Raspberry Pi especially, which is currently getting better. And I had made some ARM v5 images before for the Raspberry Pi, which I have on my own servers because I didn't use the standard Kiwi image building mechanisms. Yeah. And these slides are hard. Yeah. So one thing I would have liked to show is how to do it. It's actually very easy. You install the OSC package on your x86-64 machine, and then you do a checkout, which is OSC checkout openSUSE factory ARM, which is openSUSE colon factory with a capital F and colon and ARM with all capital letters, and then package name. For example, Frozen Bubble is a nice package, and then it creates a checkout of the source code. And then you change into this directory and call OSC build. And OSC build takes some extra parameters behind to tell it which architecture you want to build. And there you say, for example, ARM v6 HL, ARM v6 L, where the first is the name of the repository, which is just a string. And the second is actually the architecture to build. So, and then it will download all the binaries, the compiler, the bash, the RPM, which you need to build, and it will install a change root under var temp build root, and then it will change into this change root and do all the building with a normal RPM build process here. And on your x86 machine, it will use qemu with a nice, with this magic. There's a bin format misc magic where you can tell the kernel if you see a binary that starts with this string, you need to use this emulator to call it. And there's this script to set up this kernel magic, which is something like qemu bin format conf.sh, and with this magic set up, you can just change root into this directory, and when you then call uname-a, it will tell you that you are an ARM machine, even in reality you are just Intel. but the emulation does this. So, and in there this building happens, and at the end you just get a binary out there of the build process. So what is it good for? For example, if you see some failure, you see, oh, there's a package failing only on ARM, but on x86 it's normally working. You can do this checkout, verify on your local machine with OC build where it's failing, and analyze in the change root what is the real problem behind it. And once you know it, you do your fix and do a submit request like you normally do contributing in factory. And when the submit request is accepted to factory, it should be getting built automatically on the server side again, and then it should be working and be better. And everything will be happy and nice afterwards. Yeah. So we have a nice way to contribute to ARM, even if you don't have ARM hardware right away. That's a nice thing there with this emulation. Yeah. So any questions? 12 minutes. Yeah. So would you know how to build ARM now? Yeah. Great. There's a question. Microphone? You just?
So about compatibility, if I have a package for x86 and I want to convert it to ARM, what must I do to, how should I do it?
You need to recompile the source because it's a completely different architecture. So you say, take the source code of your package, the source RPM, for example, and yeah, usually you will have this package in OBS already, and then you just do a checkout, like OSC checkout, this package from OBS, and then you say OSC build. But if it's not in factory, it's a bit more difficult because you have to give -- alternative project openSUSE factory ARM as an additional parameter to tell it that you wanted to build against that project with these dependencies. And we have a portal page on en.opensuse.org/portal:ARM, and there's a link to how to build with this alternative project methodology. So, so in general, you take your source code, you build for ARM with the compiler that creates ARM binaries, and then you have your ARM package instead of an x86 package.
So you don't need to modify the source code?
Normally not. Most packages just build, and sometimes there are some problems. For example, if you have special types like a character, and on Intel a character is unsigned as a value between 0 and 255, and on ARM it's signed, so it's a value between -128 and +127, and these small differences between definitions and compilers can break things, but normally it's okay, and it just works.
Okay.
I have a question too. What about if the source use some command from AVA, for example, AVA? Okay. So if you use some commands like AVX on the source, when you build it for x86, it's easy to compile for ARM then? My English is not good.
Yeah, usually it's nearly as easy, like make install, the usual things.
You mean extensions that are only available for an
Yes.
Binary stuff?
No, the command extensions of the x86 and AVX or
MMX? Or what? Eh? Not sure. Yeah, you don't have special CPU instructions from Intel like MMX or SSE on ARM, but ARM has its own vector instructions called Neon, which is only available on newer ARMs. Yeah, but usually the compiler cares about that, except if you have assembler code, and if you have assembler code that's specific to x86, you have either to provide a generic C implementation that just does it in C code, or provide ARM assembler instead, which is very hard in the end, because there's not just one ARM platform, but there's ARM v5, ARM v6, ARM v7 with some extensions, and some extensions are only optional, because there's not a single ARM CPU, but there's an ARM core and some ARM extensions that silicon makers can add or cannot add. So it depends a bit. Yeah, but usually you just say your compiler, here's my C code, and compile it, and you don't want to use assembler these days, except if you really, really must. Okay.
Just to add something, if you are interested how it looks like, how the port is done, it's all done in the open build service. In the current development project is openSUSE factory :ARM. So everybody can go there, can check what the status is, what's currently broken, and there are also several projects which produces images for various hardware.
Yeah. So time is up, or one last question.
I would like to know, are you working on a kernel flavor for ARM?
Yes, there are multiple kernel flavors, because every ARM board needs its own kernel, because there's no PCI bus where you can query what hardware is there. But it's mostly one chip which has everything built in, and you need to have a special kernel for this chip usually.
Why you can't have one kernel for all ARM devices implemented?
Yeah, it's a work in progress. They're
yes, that's the question. What's the status of this work?
Yeah, the code name is device tree, where you have some description for a certain layout of hardware, but I just know it's improving, but I think you can run five, six different boards with one kernel, but you still have all the other old hardware with their special separate kernels.
And what is the status in openSUSE? Is someone working on some unification of kernel? Or the things you said are mostly done in upstream?
Yes, most of it happens upstream, but we have one kernel package for multiple boards, and then we have the special flavors, which you recognize by the dash panda board or dash IMX something, so the chip specific extensions on the end.
Thanks.
Yeah.
Any more questions from IRC? No?
Okay, so thank you all for attending. Yeah.